All right, chapter 7, talking about systems and matrices. Starting off on page 150 of your notes packet, looking at 7.1, we're looking at systems of two equations. Recall from algebra that a system of equations can be modeled by graphing lines, and the solution to a system is where those two lines intersect. So we could have one solution, we could have no solutions, or we could have infinitely many solutions depending on how those lines are. And we're going to see some examples in this section. So our first objective is to solve the systems of two equations by substitution, elimination, and graphically. Those are the three methods that we look at. And we can actually use our calculator to solve these graphically. So, how to find the point of intersection on your calculator. Remember, the system of equations solution is the point of intersection. So, first we want to graph the equations. And you're just going to do this the normal way. Go into the y equals. For y1, you're going to put your first equation. And then hit enter. And then y2 is going to be your second equation. And then you're going to hit graph. So then your calculator will show you both equations. So for example, if we're looking at our calculator and you go into y equals, and I'm going to delete my equations. I'm also going to go up and make sure that my plots are turned off, so none of those are highlighted. That way I know that the only thing that will be graphed is my lines. And I'm just going to use the example 5x and, we use 5x and the example x plus 3. Okay, so then I hit graph and I can see those two lines. I'm going to go back into my standard view so that I can see it more clearly. And then in order to find that point of intersection, just like finding the maximum, the minimum, or the zero, we're going to go into the calculate. So we're going to go second calculate. Notice it says calculate right there. Okay, so if I move my calculator over to the side, and I move my notes over a little bit. Let's see if I can get these on the same screen. Okay, so we did second, and then we hit the trace button, which was really to calculate. Notice the fifth option here is intersect. So we're going to hit option 5, which is intersect. And then it's asking first curve. So it's on my blue curve. I'm just going to tab over left and right arrows in order to find the intersection. Using the arrow keys. Okay, so I highlight my first curve. And then hit enter. And then the second curve. Enter. And making sure that the highlighted point is approximately at the intersection. And then it says guess. And then hit enter. And it will give you the point of intersection. So, minimize my calculator. The results are x equals 0.75 and y equals 3.75. So we get the point 0.75 comma 3.75 would be the answer. So this is an example of the results that you could get. Okay, now we've talked about in class how to find zeros on your calculator, but here's formally the steps. So we start out the same way. You're going to graph your equation, and this time you could have just one equation. So graph equation, which is y equals, y1 equals your equation, and then you go to graph, and then your second step is similarly you're going to do second trace, which is really to calculate. But this time, instead of doing intersect, so I'll just do one line, second, calculate. Instead of doing intersect, we're going to do option 2, which is 0. And then we're going to do left bound, right bound, and guess. So for left bound, I want to make sure that I am to the left of the 0. So if it's right on top of the 0, you can't be sure that it's to the left. So you want to go ahead and click the left button until you're positive that it is left of the 0. And what I mean by left is an x value that is less than your 0. So here, and then right bound, I'm going to go up, and then the 0 is a guess. So very similar process to finding a maximum and a minimum, which we've already written in the notes. So writing that on the notes packet, we want to now find the 0 using the left and right arrow keys. We do left bound, left of the 0, left of the x-intercept, and then enter, right bound, enter, guess, enter, okay, and then it will give you the results. So it will give you a point. Now in this case, the point is 0, 0. It won't always have a 0x value, but because it's a 0, it should always have the 0y value. Results will be x equals some value, in this case 0, y equals 0, and then that gives you the point 0, 0. Note your y value should be 0. That is what a 0 of a polynomial is. It's when the y value is 0. Okay? And then the last step is to repeat for any other x-intercepts of the function. So if you have a higher degree polynomial, you might have multiple intercepts, and you have to calculate the 0 for each of those intercepts. All right, let's look at an application of this. In example 1, we want to, it gives us that the system has one solution, and we want to solve the system by graphing, substitution, and elimination. So part A, graphing. And for that, we can use our calculator. But in order to use the calculator, we have to solve for y, or f of x. So we get 2x minus y equals 10. add y to both sides, subtract 10 to both sides. 2x minus 10 equals y. So now that's something I can type into my calculator, y equals 2x minus 10. For the second equation, 3x plus 2y equals 1. Subtract 3x from both sides. 2y equals negative 3x plus 1. Dividing by 2, y equals negative 3 halves x plus 1 half. So let's go ahead and put that into the calculator. Y equals, our first equation is 2x minus 10, enter. The second equation is negative, make sure you're using the negative and not the minus, 3 halves x plus 1 half. And then I hit graph, and I'm looking at these two lines, and I want to find the point where they intersect. So if I'm looking here on my paper, I can draw these lines as approximately like this. And I'm looking for that point of intersection. So, second, calculate intersection using the right arrow key until it's close to where they intersect. Enter, enter, enter. And my point of intersection is given as 3, negative 4. Okay, so that's my x value is 3 and my y value is negative 4. All right, then part B is asking to solve by substitution, which means I want to find the value of one of the variables and then substitute that into the other equation. So if I'm starting with 2x minus y equals 10 and 3x plus 2y equals 1, I can go ahead and solve for y pretty easily, and I already have it from above, that y equals 2x minus 10, and then substituting that into the other equation for y. 3x plus 2 times the quantity of 2x minus 10 equals 1. So 3x plus 4x minus 20 equals 1. That was distributing the 2. 7x minus 20 equals 1. 7x plus 20 on both sides is 21, so then x is 3. Then from here, I want to substitute that back in. I need to find my value for y. So this equation is already solved for y. I can do y equals 2x minus 10. So y equals 2 times 3 minus 10. Y equals 2 times 3 is 6 minus 10. Y is negative 4. So I get the point 3, negative 4. I'm going to go ahead and box my answer up here as well. All right, and the last piece is by elimination. Now, elimination means I'm going to use addition of the two equations in order to eliminate one of the variables. So, elimination, I have 2x minus y is 10, and 3x plus 2y equals 1. Now, in order to eliminate one of the variables, I want their coefficients to be opposites. 2 and 3 are not close to being opposites. There's no factors that they have in common. However, here I have negative 1 and 2, so if I just multiply negative 1 by 2, I already have that they're opposites. So if I take this equation, multiply it by 2, what I'll end up with, and make sure you multiply each term, so 4x minus 2y equals 20. I'm just going to go ahead and copy over the second equation. 3x plus 2y equals 1. And then I'm using kind of function addition. So 7x plus 0 equals 21. X equals 3. And then just like before, I have to substitute that back in order to find my value for y. Now, it doesn't really matter which equation you use. However, I'm going to use the first equation just because y doesn't have a coefficient there, so I think it will be a little bit easier. sorry about that, the recording got cut off. So what I've done is I've taken my value for x and substituted it into the first equation. So we get 2 times 3 minus y equals 10, and then solving for y. So 2 times 3 is 6, subtract 6 from both sides, and then divide by -1 on both sides. And we end up with this same value, the same point, 3 comma -4. Now, since we're solving the same system of equation all three ways, we should have the same answer for all three methods, and we do. On the next 2 pages, examples 2 and 3 are the same process. However, in example 2, there are no solutions. Now, if we're looking at a graph of 2 lines that never intersect, those 2 lines have to be parallel. So, parallel systems have no solution. Okay, and then in example 3, it says we have infinitely many solutions. And if we have 2 lines that have infinitely many points of intersections, then those 2 lines have to be the same line. That was a little bit. Those 2 lines have to be the same line. So a system containing 2 of the same line has infinitely many solutions. Okay, and the way we write our answer when there are infinitely many solutions, because it's not just negative infinity to infinity, but we would say it's the set of all points x, y, where in this case, those 2 equations, if it has infinitely many solutions, those 2 equations have to be the same line, so it doesn't matter which one we pick. So 4x minus 5y equals 2. So all of the points on that line are part of the solution. Okay, as far as showing this graphically by substitution and by elimination, I'm going to leave that as an exercise for you. All right, on the next page, looking at example 4, our goal or our objective is to solve applications involving systems of 2 equations. So we're applying this. So one of the ways that we could see this is if we have dimensions of a rectangular garden with a perimeter of 100 feet and an area of 300 feet, and we want to find the dimensions. So I'm going to start by drawing a picture. Okay, the area is 300 and the perimeter is 100 feet and feet squared. Okay, I don't know the dimensions, so we'll call this x and this y. But I do know their relationship. So the perimeter, remember, is 2x plus 2y. And we know that that equals 100. So I could actually simplify this. 2x plus 2y equals 100. So dividing by 2, x plus y equals 50. And we also know that the area is length times width, so xy, okay? And we know that that is 300. So now I have a system of equations. I have x plus y equals 50 and xy equals 300. And I put the little curly bracket to tell me that it is a system of equations, that I want both of these to be true, okay? Now, in order to solve this, I can use graphing, I can use substitution, I can use elimination. I'm going to use substitution, so I need to solve for one of these variables. I'm going to choose to use the first equation and to solve for y. So we'll say that y equals 50 minus x, and then I substitute that into the second equation, so I get x times the quantity of 50 minus x equals 300. So that's 50x minus x squared equals 300. So now I'm solving a quadratic equation. Bring the camera down a little bit. So I want my leading coefficient to be positive if possible, so I'm going to subtract both of those terms to the other side. So x squared minus 50x plus 300 equals 0. So I can solve this either by factoring, quadratic equation, or graphing. And whichever method you choose to use, it's not factorable on rational numbers. So quadratic equation or graphing calculator would be the way to go here. You'll end up with x equals 6.97 and x equals 43.03. So if x equals 6.97, you can do xy equals 300. So 6.97y equals 300. So then y equals, and you'll end up with 43.03. And similarly, if you substitute this way, you'll end up with y equals 6.97. And so we know the dimensions of our garden. It doesn't really matter which one I had called x and which one I had called y. So the dimensions of the garden is 6.97 feet by 43.03 feet. Okay, realistically, if you were a landscaper and you were doing this, you would probably say that the garden is approximately 7 by 43 feet, because that 0.03 feet would not show up on a measuring tape. It would be too insignificant. However, it would give you an area of 301 feet squared instead of 300 feet. And that's why we ended up with those numbers. Okay. On example 5, we want to solve algebraically and then support it graphically. So we're going to check our answer by graphing it. Again, I'm going to choose to use substitution because I see that these are both already set equal to y. So algebraically, I'm choosing to use substitution. I'm going to substitute 3x for this y. So 3x equals x cubed minus 6x. Subtract the 3x, so x cubed minus 6x minus 3x is 0. X cubed minus 9x is 0. In order to solve for x, I want to factor, and they both have a common factor of x. So x times x squared minus 9 is 0. This is one of our special polynomials. It's a difference of squares. So I have x times x plus 3 times x minus 3 equals 0. Now using the zero product property, I know that one of those, at least one of those factors has to equal 0. So x is 0, x is negative 3, or x is 3. Okay, I end up with the set of negative 3, 0, and 3 in ascending order. To check this graphically, I would graph these two lines. So if I pull up my calculator, and I clear my graphs, and I say my first line is x cubed minus 6x, and my second line is 3x, and I want to graph those, I end up with this line and this cubic function. Okay, we know that this point is 0, 0. We can find that this point is 3, 9, and this point is negative 3, negative 9. We're looking for our x values, so it gives us all three of those x values, which confirms our answer. So our solution, our final solution, is negative 3, negative 9, 0, 0, oops, and 3, 9. All three of those points satisfy that system. All right, on the next page, example 6 is very similar. I'm going to leave that for you to do. Notice it doesn't say you have to do it algebraically. This time you can just use your graphing calculator, and natural log is a function available on your calculator. All right, for example 7, we're looking at a table that shows expenditures for dentist and health insurance in the United States. So Notice we have years, we have dentist, and we have health insurance, okay? I'm going to let X be, whoops, the number of years since 2000. Okay, so if you look on the next page, the first thing that we're looking for is the linear regression. Let's do this. I can't show the table and the questions at the same time, so I'll just show the questions and also have your table so that you can refer to it. So find the linear regression equations for the expenditures for dentist and health insurance in the table. So what that means is that we want into our calculators to type these as our lists. So if I call this L1, my X values will be 1, 2, 3, 4, 5, 6, and 7. And then this will be my L2, and this will be my L3. Okay, so let's go ahead and type that into the calculator. Now to access our lists, we're going into Stat, Edit, okay? Now I have it typed in. You don't need to watch me type all of those in, but remember, you want to make sure that all of your lists end at the same kind of line so that you can make sure that each of your points has a value, okay? And make sure you're careful when you're typing them so that you can double check back and make sure that you didn't miss any digits or decimal places, okay? You can go ahead and pause the video to take time to type those in. And then once you have those typed in, what we want to do is find the regression. So that was in Stat, Calculate, and it's telling us it's a linear regression. So we're going to go to option 4, which is the linear regression. Now, first we'll do the linear regression for dentists. So that's list 1 and list 2. And we're going to go ahead and calculate. And what we end up with is we have, for the dentist, we have y equals 4.83x plus 61.5. Okay, and then we also want to find health insurance. So we are going to, again, Stat, Calculate, Linear Regression, which is option 4, but now we're going to use list 3. So down over the 3 button in blue, you'll see L3, and that's what we want to use. Okay, and then we're going to go down and calculate, and we get that our second linear regression equation is that y equals 11.43x plus 78.49. Okay. Part B on the notes pages says to, let's see, I'll keep those equations in frame. Says to use the models from part A to estimate when they'll be the same as, so when the expenditures for dentists will be the same as health insurance. Okay, so in order to do this, we can go ahead and graph those 2 lines. So my first line is 4.83x plus 61.5. Enter. The second line, 11.43x plus 78.49. Now, I'm also going to go up here and turn on my plot 1 and 2, okay? And in order to make sure those are plotting the correct points from my table, I want to go into second stat plot above the y equals and look that plot 1 is doing L1 and L2, and then that plot 2 is doing L1 and L3. If it's not set up to do that, you might need to go into the settings and go to the Y list and change it to L3. The same way that we did earlier, you're going to do second 3, which is the L3, so your list number 3. All right, so now what we want to do is we want to go into our window and make sure we are looking at an appropriate window. According to our table here, our x values range between 1 and 7. I'm just going to leave it -10 to 10. I'm not going to edit that yet, okay? But our y values are high. So I'm going to go ahead and change the y maximum to 160. Okay, because I know I need to look at least to 153. And now I'm going to go ahead and graph it, and notice the graph, because of the way we had it set up, does both of the lines as well as the scatter plots. Okay, now the question was, where do they intersect? So we're looking for that point. So we do second, calculate, intersect, and we go down to where they intersect. Enter, 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 and they intersect at this point. So the video cut out a little bit, so I have already drawn the graph and I've labeled it with the point, but now the question is, what does that mean? So we have this point, we have our x value and our y value, okay? Now remember, x was the number of years since 2000. So if we have an x value of -2.57, that means it was 2.5 years before 2000. So -2.57 means 2.5 about years before 2000, which makes it 1997. Okay? And the y value is 49.07, so that's about $49 billion. Okay, so I'm going to write the answer over here. In 1997, with $49 billion in ION, in expenditures. That's when they were the same. Okay. Example 8 is very similar to the one that we just did. Actually, it's easier because it's already solved into the lines, so you don't have to start with the scatter point. So you're going to go ahead and do that one on your own, and then make sure to summarize what you learned from this section in the last box.